Should I start? Yeah, go ahead. Okay. So hello everyone. First of all, this is not my talk. I've been receiving this talk because my colleague didn't make it to get the visa on time. So I'm sorry, I don't know anything about Kubernetes. I'm usually more into low-level stuff, kernel and embedded. But I will deliver the talk with the notes that I received, and if you have questions, you can directly direct it by email to my colleague. I wouldn't be able to answer. I'm sorry for this in advance. Okay. So, before getting to the architecture and principle of the KubeOS, let's define what it solves. So there is a cloud-native development that is encouraged by Docker, Kubernetes communities, and many infrastructure is being cloudified. But some of the problems with the general-purpose operating systems reappear in these cloud-native environments. So you have container management, workload scheduling, automatic service deployment, rollbacks of updates, and so on. That's all capabilities that are provided by Kubernetes, but it is unable to control the cluster nodes operating system directly. So the first problem in cloud-native environments is the desynchronization between OS and Kubernetes that are managed and controlled completely separately. Also, Kubernetes, like the operating system management, needs upkeep, upgrades, user access control, all these things. And then you can have like the ops operation guys, or operation people, sorry, that need to complete redundant tasks between the two systems. The maintenance are therefore poorly synchronized usually, and the upgrade and modification of the OS components can affect the availability of the OS, and which require additional monitoring from Kubernetes. So an example is that you have operation staff that must block the nodes to stop new workloads from arriving in order to upgrade the OS without interfering with the Kubernetes. And after everything is clear and everything is updated, you can unblock the node again. So this makes it complicated and expensive. So another issue is the OS version management. So if you have a standard package manager and you can add, remove, modify packages independently on the OS, at the beginning you have an image which is clean, but then it starts differing from your different instances. So you have like what they call OS version splitting. So you will have different packages installed on different nodes. The version of these packages can also differ, security updates and all that stuff. So you have this divergence that appear over time. So if you want some integrity and consistency that you want to ensure for your OS nodes, this can harm this constraint. And yes, so if you want also to update from to a major version, it's also more difficult. So other people have worked on this problem. So rebuilding the operating system is an approach that has been taken to solve these problems. So previously, you have many technology packages that are part of the OS that are moving to containers. So the guest OS is less reliant. We rely less on the guest OS. So it can be replaced by a lightweight operating system with less services that are on and so on. So Container OS, the lightweight operating system designed to run containers. So like on the figure on the right, there is a host OS, and it's not the OS running inside the container. So you have three important aspects: minimalism, immutability, and atomic updates. Minimalism, it means that you will only include what you really need as components in the host OS. So the container OS requires the Linux kernel, container engines like Docker, Containerd, and security mechanisms such as SE Linux to ensure the security. And other applications that are run in containers are run in containers because you don't need it in the host. And this can also reduce the attack surface because you have less in the host OS. Immutability is that you use a read-only file system that can be configured at the start of the deployment, and that also reduces the risk. And the atomic update is you do the upgrade for the entire OS and not individually for packages. So the core OS was started in 2013 and was the first widely used container operating system. You also have systems like AWS BottleRocket, Flatcar, and Container Optimized OS. Where am I here? So KubeOS, it's a container operating system built on openEuler, which is a distribution maintained by Huawei. So KubeOS' main design concept is to use Kubernetes to manage the operating systems. Once you have KubeOS that has been installed on a cluster, the user only needs the kube control command and YAML file on the master node. The OS of the cluster worker node can be managed, and this OS on KubeOS is connected to the cluster as a Kubernetes component, putting it in the same position as the other resources in the clusters, and containers and operating system can just be managed in a unified way through Kubernetes. So openEuler-based reconstruction is used so that the operating system can be updated atomically, like to avoid the problems I introduced before. So now we are going to go a little bit in more depth about KubeOS. So the first feature is the ability to manage the OS through directly Kubernetes. So we use API extension, custom resource, CRD, to the design and registering in the cluster. We use Kubernetes operating framework to create a customized controller for the OS to monitor and manage it. Then this Kubernetes operating framework, we use it to create custom. This already said. So the user only need to modify this CR, enter the expected OS status to the cluster, and the KubeOS and Kubernetes handle this. And you only have to manage it in the control plane. So the next one is atomicity management of the OS. KubeOS upgrade is an atomic dual zone upgrade. It does not include packet manager. The change of each software package corresponds to the change of the operating system version. Then the OS version corresponds to a specific OS image or RPM package combination. Each software update, as shown in this diagram, is an OS version update. So you avoid the version splitting problems, and the cluster nodes remain consistent at all times. So KubeOS is lightweight with unnecessary components removed to reduce the attack surface and enable faster startup and upgrades. So this is a diagram of the KubeOS overall architecture. So you have two main parts. The first with 3 different components: OS operator, OS proxy, and OS agents in the red box above the diagram, which are used for Kubernetes cluster docking, complete OS monitoring and management. And the second part is the KubeOS image creation tool. The user can use KubeOS scripts to generate KubeOS images from the openEuler repo source, which supports the generation of container image, virtual machine image, and so on. So the 3 main components I mentioned, like OS operator, proxy, and agent, are critical to the ability to manage cluster using Kubernetes. The OS operator and proxy are the operators we mentioned earlier. The OS operator will be deployed in the cluster as deployment and daemon sets and will communicate with Kubernetes to issue upgrade instructions. The operator is a global OS manager that monitors all cluster nodes. When a new version of the OS information is configured by the user, it determines whether to upgrade and sends the upgrade task to each node. The proxy is a single node operating system manager that monitors the current node information. When the operator sends the upgrade notification, it will lock the node to expel the pods and forward the OS information to the agent. The agent is not included in the Kubernetes cluster. The real executor of the OS management communicates with the proxy via Unix domain sockets, receive message from the proxy, and perform the upgrade, rollback, and configuration operations. So the upgrade process, we will use the upgrade process as an explaining example. So we consider how the different components communicate and interact. First, the user configures the OS information to be upgraded via kube control and YAML files. such as OS version, address of the OS image, number of nodes to be upgraded concurrently, and so on. Then when the OS instance changes, the operator begins the upgrade process, labels the nodes that must be upgraded, and limits the number of nodes to be upgraded each time to the number specified by the user. Then the proxy checks to see if the current node is marked as an upgrade node, locks the nodes to expel the pod, and retrieves the OS information from the cluster before sending it to the OS agents. After receiving the message, the agents will download the upgraded package from the address specified by the user, complete the upgrade, and restart. After restarting, the proxy will detect that the node OS version has reached the expected version and will unlock the node and remove the upgrade label of the node. So this is the complete upgrade process. Then finally the file system. So how do we design and upgrade the file system in KubeOS? It adopts a dual area upgrade, like mentioned earlier, to upgrade the OS. So you have two root partitions. The upgrade of partition A is to download the updated image for the partition B, and then modify the default bootloader as the B partition after, and then you restart from the B by default, and the opposite happens for the next upgrade. So it's a classic dual image thing. The file system of KubeOS is read-only, which improves the security, but we also support persistent data partitions. You have a union path, which is mounted as an overlay, and the files in the image other than the user change can still be seen. There is a writable path, which adds a writable file layer to the image using the bind mount. The files in the image are not displayed, only user data is stored, and there is also the boot partition, which contains the bootloader files. So we determined the main concept of KubeOS and designed and implemented a set of components to complete the OS management. And we intend to continue completing more functions based on this process. One thing is the ability to provide a configuration. Like in the upgrade process, the configuration is delivered to the node via the Kubernetes cluster on the cluster control plane to ensure the consistency of the configurations of the nodes. And given that some of the configuration must be complete before the nodes join the cluster, more configuration capabilities to the KubeOS image creation are planned. Then there's the improved upgrade capability. We have realized the function-based OS upgrade, and we will provide upgrade strategies that user can customize, such as upgrading based on the cluster node label to provide more upgrade solutions. In addition to rich functions, we intend to improve the usability of KubeOS by displaying the upgrade of configuration process and improving the image creation tool so that user can more easily customize their image. Okay, and that's it. Sorry again for the functions, but for the question, you can always shoot the colleague an email.